So good afternoon, good evening, everyone. Thanks for joining to this webinar that title is Tensegrity Structures and Real Applications for Accessibility Platforms. Thanks for joining. Thanks to the FIB also to organize this webinar. I hope you enjoyed it. We are starting with the presentation. We have two panelists actually that are going to talk about Tensegrity. One panelist, so Valen Gómez-Jáuregui, the first one, will talk more about the conceptual concept and theory of Tensegrity. And then the second panelist, Julian Aversen, will talk more about practical applications of Tensegrity. So I will introduce Valen Gómez-Jáuregui first, and then I will introduce later on Julian Aversen. So Valen Gómez-Jáuregui received the bachelor in 2003 and the PhD in 2015 degrees in civil engineering from the University of Cantabria, Spain, and the master's science degree in architecture from Queen's University Belfast, UK, in 2004. Both theses were focused on Tensegrity structures. He worked in two companies related to research and development in industrialized drillings and management in industrial engineering. Since 2010, he has been working as part of the research group AGCAT at the Department of Graphic Expression Techniques at the University of Cantabria, where he currently holds a teaching position as associate professor. He is the author of two books, more than 30 articles, several patents and software applications. Apart from Tensegrity structures, his research interests include CAD, BIM, visual impact assessment, and augmented reality. So please, Valen, it's your turn now. You can start.
Okay, thank you very much, Abraham. Can you hear me properly?
Yes.
Okay, thank you very much to you and to FIB, the association, and the young members group. We're going to focus the presentation, as you said. Well, this is the presentation of myself, that you know that you have my contact if you need anything, or my webpage in case you want to get in depth in some of the concepts. And as you said, we're going to split this conference, the chat, the webinar in 3 parts. I'm going to try to stay in the 20 minutes so that you have time for listening to Julian, and then time for questions and discussing. My presentation is going to be organized in 5 points. First, the objectives. Then we're going to give some short definitions. I'm going to point out very slightly about the origin of Tensegrity structures, and then we're going to see some examples related to the art and the engineering, basically, and architecture. The objectives are very basic. First of all, knowing what is a Tensegrity. The best way to know how is a Tensegrity is to, I don't know if you can see my screen, but this is a Tensegrity structure, a very basic Tensegrity structure. We're going to see some of its properties, but the good thing about this structure is that you can play with it very easily. You can fold it, you can make many things with it. It absorbs very good the vibrations, and it's a pity that you cannot touch one of these models, but well, hopefully you will have a slight idea about what is a Tensegrity. Then we're going to know what they are useful for. We're going to give you the insane need of building a Tensegrity structure. If any one of you want to do it, please contact me and I will try to help you. But you will find many information on the web. And then you will have some references, bibliography in case you want to go in depth. Well, what is a Tensegrity? This is the one of the accepted definitions of a Tensegrity structure. It's a structural principle. It's not just a structure, it's a principle based on the use of isolated components, that in this case are these bars, inside a net of continuous tension. The tension in this case is composed by these wires, these elastic bands that you see in red. In such a way that the compressed members, the bars, don't touch each other. I don't know if you see it properly, but they are isolated and they don't touch each other. They are attached mainly by tension members that can be this kind of elastic bands, or they can be membranes or any other of tensed element. Very important, as you see here, the tensegrity, the outside, the boundary is composed by the members in tension. There are no compression elements around in the boundary. There are some other examples, some other definitions, but in this slide, I want you to show you another possibility of changing those elastic bands by membranes, as you see there. Many other definitions, but one of the most important sentences about tensority was given by Buckminster Fuller. We'll talk about him later because he's one of the fathers of tensority. And he said that tensority are islands of compression in an ocean of tension. Okay, the compression are the bars, the tension are the elastic bands in this case. And there we have a sculpture by Kenneth Snelson, another father of tensority. They are also called false tensority because there are some structures that look like tensorities, but they don't participate with all the definitions, all the concepts of tensority. There on your left, you can see a set of bars, but they are touching each other, and the boundary is composed by that triangle of struts or bars. And on the right, we have another example where we have a ring that is compressed and is, let's say, standing for the whole stability of the structure. When we talk about tensorities, we can talk about their class. The class can be K1, K2, or K3, or so on, being key the number of bars concurring to any node. Here, that would be class K1 because the bars are isolated. In the nodes, there is only one compressed members. But as you see in this figure, this tower, the Rostock Tower in Germany, at each node, there are two bars concurring. So we could say that this is a K2 tensority structure. Related to the origins, I don't want to give you many information. You have a lot of it on the web and in some publications, but you should know that there are 3 patents in the late 40s, and the 3 of them by Kenneth Snelson, Buckminster Fuller, and George Emmerich. There you have the images, and these 3 huge engineers and architects and artists discovered the same structure at the same time. That is a tantalizing story. I'll let you know about it. But probably the origin of that coincidence is that 20 years later or 30 years later, there was a structure by Carl Johansson, a sculptor, that was very similar to the simplest tensority structure, which is the simplex, as you see there. These are the main kind of basic structures which were made by Kenneth Snelson, one of the fathers of tensority. And you can see that they can be very basic. They can start to be a little bit complicated, be more complex. And at the end, we can have incredible sculptures in the landscape with a huge scale. And as you see, these cantilevers are incredible. Some other structures tend to imitate some arches or some towers in order to give it an application. There are some other kind of structures that can be a little bit different. As you see in this kind of, in the basic tensority structures, we usually have at each node at least 3 tendons, three tensed members. Here or here, we can see that we have 3. And in these images that we see here, I don't know if you realize, but they are at this node, at this bar at the end, there are only two elastic bands or two strings, which make these sculptures very particular. Well, these are not very different to these ones, but this is composed by normal structures with three elastic bands at the end of the structures. Some other examples with bending moments. One of the advantages of Tensority structures is that usually, as you have these straight elements, there are no flexions or torsions or anything like that. It's just compression and tension. But in these sculptures, if you bend the element, the conditions are different. We have some other examples of artistic pieces, in this case by Tom Flemmons, with some sculptures that remind a little bit to Calder. Some of these structures started to evolve and tended to giving some hints about the possible structure of the spine, of the human spine. As you can see there on the right, that is a model trying to replicate the spine by made of a Tensority structure. Some other examples of biotensority models. Biotensority is, let's say, a deviation of tensority, trying to find in nature and in the anatomy different examples of tensority principles. And finally, Flemmons also, let's say that he created some very nice furniture, chairs, tables, and toys composed by Tensority structures. As you may have seen, these kind of structures have several advantages. One of them is that they are very light, because some of the noble compressed elements, bars in a conventional structure, are replaced by tendons. They are efficient, they are very flexible, as you can see. You can fold them very easily. They absorb vibrations very easily. They are more transparent than some other structures with more elements or thicker elements. They are very aesthetic. And finally, one of the main advantages is the deployability that you will see in Julian's presentation. There are some other examples about their applications, like in furniture for chairs. There are many possibilities, as you see on the right. So there are several patents too. You can find tables, you can find lamps, and some other applications related to animals. On the left, you see an aviary in London, and on the right, you see some cages for fish that are composed by Tensority structures. Some other applications are related to the space. There on the left, you see a boom structure that is deployable and tends to be wants to be an antenna, kind of antenna that can be deployed. You can bring it to space very, very easily in a very compact space, and then you can deploy it once you are there out in space. And some other examples of parables and other elements. In civil engineering, we have several examples too. Maybe the most iconic is there on the left, the Gorillapod Bridge in Brisbane, Australia. As you can see, some of the elements don't touch each other, some of the bars don't touch each other. And it's true that the deck is not exactly a Tensority element, but this bridge is one of the first and most important applications of Tensority structures to civil engineering. Some other proposals for bridges, and there on the bottom you can see a very nice project made in Lausanne, where a footbridge is proposed to be created by means of two parts that deploy from each side of the river or of the span that you want to cover. In architecture, there are also some examples that you can see. Then some roofings, some domes, stadiums, or omnisport holes. And finally, well, some other examples of different kind of projects or proposals. And maybe one of the most attracting is the one that you see on the bottom, made by Gunnar Tibert, where he tried to change or to replace the typical aerial electricity lines by Tensority structures that could be lighted by night. Now I'm going to focus on the double-layered Tensority grids. There are some kind of grids composed by two layers, one on the bottom, one on the top, one on the bottom, composed by wires. You have also some web wires going in the middle, and there are also some struts composing the whole structures. There are different proposals from the 50s in the 3 patents that were proposed by the fathers of Tensority. We can see some of these double-layered Tensority grids. We can also see in some years later some other proposals made by different authors, but mainly Pugh and Villeneuve proposed this kind of grids. Very importantly, Ariel Hanover and René Motreau in the 80s proposed some other examples where they also focused on the tensional efficiency of these kinds of grids. Emmerich in France also created or designed different typologies. Wang Bingbing wrote a whole book about different typologies, and the grids were also very important. Kono and Kunieda created a different kind of structures, building some prototypes where instead of using prisms, they used pyramids, truncated pyramids. And finally, well, most important because Julian belongs to the University of Montpellier, and this research group, led by René Motreau, created the Tensart project. And there you can see some proposals that are going to be explained by Julian later. And well, these are some other variations of this project, of the Tensart project. Well, in the last years, there were also some other projects. And here, I don't know if I can reproduce an example that we did in Limerick, in Ireland, with a different kind of module, which is the one that you see there. And here we can see the construction process. This is, well, this part is prototype of 2 by 2 meters using strings instead of wires. There is the folding state. And then we reproduce that for the 4 by 4 structure. The wooden base was configured to set the exact position of the nodes at the bottom. And once that the structure is configured, we started to charge it, to load it, to see the resistance, which was very good. And finally, we did the folding states. And there is the final structure once it's deployed. Folded. I'm nearly finished. I just leave you there some webs that you can check, that you can visit if you want to find out more about these kind of structures, and some of the most important books that I have already mentioned, and some others that you can find very easily in any library. And I think that's all by myself. I finish with this. Thank you very much, Abraham.
Thank you, Valentin, for your presentation. That was great. I already knew some videos, some pictures from you, and I'm always happy to see that again. So I forgot to say at the beginning, so welcome to the people that join later on or after or start today. Now is the turn of Julian Aversen. So after his presentation, we are going to do this questions and answers turn. So you can address your questions and then the panelists will answer you also for your curiosity about Tensegrity. So now is Julian Aversen. He obtained a master's degree in teaching at the YMG Webinar in 2000 and a PhD in civil engineering at the University of Montpellier in France in 2004. He worked at the Blaise Pascal University and is now a lecturer at the Laboratoire de Mécanique de Génie Civil, LMGC, of the University of Montpellier. He is currently head of the civil engineering department of the EIUT of Nîmes. As a member of the CIGECO team, his research work focuses on the design, control, and dynamics of lightweight, deployable, and Tensegrity structures for civil and space applications. His interests are oriented as much towards numerical and experimental or even biomimetic approaches for the modeling and design of innovative, dynamic, and evolving systems. So thank you, Julia, for participating. You can start.
Thank you, Abraham. Welcome, everyone. Thank you for attending. I present you an application about accessibility platform of a particular Tensegrity structure that Valen presented earlier, which is the Tensority concept. So I'm Julian Aversen, but this work was done also with Issam Razmi, our FIDI student, and my colleagues, Jérôme Kiran and Frédéric Jamin from the laboratory. I just made a slide, but I don't stay too long on this. We are here in Montpellier, and our lab is interested in mechanical interaction, multi-physics coupling, biomechanics, imagery. We do either numerical studies as well as a lot of experimental studies, very interesting, and also Tensegrity and deployable systems. So the concept of the context of this, what I'm going to present, is a project proposed by architects on the constat that there is no solution for people, disabled people, to go to the sea in total autonomy, in full autonomy. So this project, POSEIA and C4All, wants to improve that by providing solutions to accessibility for all, full autonomy, but also respecting the littoral law, which consists in setting up the structures only in spring and dismantle all of that in autumn. And to be viable, it must be fast and easy to apprehend by the local operators, either private operators on the coast or public cities. So the concept is sketched here. It's a zone with access via the road, and also some buildings to have the possibility to change, and the structure in the sea with elevators, and which allows to make some recreational activities for the disabled. Okay, so what we did with this concept is to propose a solution for the platform part, and we propose a deployable platform on which we can install autonomous equipment like elevators. Our inspiration is a solution that exists in France. It's un fauteuil à la mer. This is this structure, which is next to a bar and to a beach, a private beach. And on this structure, there are a lot of equipments like water elevator, that can be used by the disabled people, as you see on this picture, and in relative autonomy. So our goal is to make the same, but dismantle completely deployable and dismantleable, so as to let the site completely clean after usage in winter. So the platform is about to be assembled by Tensegrity grid models. Tensegrity is a topology that Valen showed you. I will present. I will go back on it. So the principle is to have some modules that can be deployed from small bundles, and we can arrange these modules to build any kind of platform. And so I will talk, this is a summary of my presentation. I will talk about the topology and the interest of foldability with this solution. The adaptation to support some platform, and the modularity here, and the problems in the design that are consecutive. And finally, the experimental part with fabrication and setting up. So to remind you about Tensegrity, Tensegrity is a concept proposed by René Motro in the late 90s. So it was built and concretized here in Montpellier in 2000. You have here a photograph of the great grid, which is 80 square meters. And the principle of Tensegrity, it's a waving of struts, just like a fabric. So it's a class 2 Tensegrity system, because you have 2 bars at each node, except from the border nodes, which we receive only 1 bar. So the struts, I talk about bars, but it's struts, are surrounded, because it's a principle of Tensegrity, by a continuum of tension, which is formed by 2 layers of cables, and a boundary cables that finishes the stitching around, and vertical tensioners. So to give you an idea of Tensegrity, another idea of Tensegrity, it just works like inflatable systems. And if you have already used paddles, inflatable paddles on the sea, you'll see that the structure is quite the same, with vertical tensioners, actually fabric vertically connecting the 2 surfaces, and the pressure inside is actually the struts here in our case. You have here a map, a color map of the self-stress inside an elementary module. Self-stress is the state of internal forces inside the Tensegrity system that keep the cable tense and that allow the system to get its rigidity. If you don't have the pressure or the tension inside the cables, you have something that is completely loose and that is not usable structurally. Okay, so about the foldability, Tensegrity is really convenient. As you see on this this picture, it's only sufficient to detach just a few elements. Actually, here the vertical tensioners, to eliminate any self-stress in the system. So, like opening the valve on an inflatable system, and you have no pressure, no tension, and you can fold it in a small cylindrical bundle. And this diagram shows you the gain in volume that you have when you fold the system. To use it as a platform, we have to put on it some plates, deck plates, but the Tensegrity topology doesn't offer enough supports. So if you do that simply, you have some part of the deck that will be in cantilever. So in this solution, particular solution, we add some additional substructure that are just formed of bar and vertical bar and diagonal bar. And the principle, the idea of this substructure is to redirect the vertical load on existing nodes. So on this node here, you see the force goes directly in this node, and then the distribution of force goes to the supports. And for the corner node, it's the same. The force goes diagonally down on this node, and to be equilibrated at this location, you need to have a cable that is attached to this node. So this is the static equilibrium principle of this additional structure. The modularity is really important in our solution because we cannot build a foldable platform of a large surface in one piece. It would be impossible to manipulate or handle it. So we work with several small modules that we attach border to border. And with the tensor, which is a regular waving, you have naturally modularity, but you have to pay attention to the border and to the direction of the pattern, actually, of the bars and the nodes. Actually, you see here that you have a pattern of vertical of layer cable on the surface with cables turning in this side. And to be able to connect correctly, you have to have the inverse pattern on the other side. It's just a small work to do when building and when designing a platform by juxtaposing these modules. But in this case, after that, you have a complete continuous set of vertical support for the deck. So this is a problem that I was mentioning. You cannot do that because it's completely inefficient and you don't have any support on the side. You have to invert the two sense of the modules. And we have also the possibility to connect some modules that have different heights so as to adapt to the profile of the land. And you see here how actually this solution works. It actually works by being supported on the ground. Obviously, it's not floating in the sea. So we can adapt and make a rigid structure posing in the land, and we can adapt to the profile of the land. So on the design part, using these constraints, I won't go into detail for bar and cables, which are standard elements, but the real challenge in every tensegrity system is the nodes. Because they have to ensure convergence of forces, and we have here many elements for some of these nodes. In our case, they must allow folding by allowing the bars to rotate relatively one to another. And we also want to minimize the complexity of the solution so as to have only 3 types of nodes, which are represented here. Center nodes, we call it center, but regular nodes, and border nodes and corner nodes that connect cables with 2 different orientations. So you have here some drawing of the mechanical models, and you can see the complexity of the design respecting all of this. On the design, we have also to dimension the sections of the elements, the cable and the bars. So for that, we have to deal with the self-stress that we will have to introduce in the structure, and also the variation of internal forces during usage when you have a vertical load on your platform. So here is the representation of the internal force, and where you have in the horizontal axis the number of the element, and we have classified the elements. So you have to have the bars here, the struts, and all the tense elements, cables of the inferior lower layer, the upper layer, and all the other elements. And you have here the classification of the different elements. So when we use self-stress system, we do that by shortening the tensioners, by rotating them. It's just a system of screw. And the shortening is just, it's very small, and it's the order of only a few millimeters. So the response in the structure is quite linear in this case. So don't worry, I won't present some complicated charts, but just internal forces bar diagrams. And about the design, we have to pay attention to and they optimize also the position of the supports. So here the first study on different kind of supporting possibilities. You have here in black the supports in the corners, or just on the four lower layer nodes in the center, or here a mixed combination of the two previous solutions. And we have here the consequences when loading these modules by a force of 3 kilonewtons per square meter, and the self-stress initial of 0.2%, and the consequence in internal forces and also vertical displacements. And we see that with this solution, we minimize vertical displacement. So this is the optimum solution for this small module. The other solutions are less optimal, and particularly this one with an increase in forces. We also were interested, well, this is the same, but presented differently, with the sum up of the different families. We're also interested in the same study by optimizing the number of supports, because the creation of the support in the sea is quite laborious, so we have to minimize it. And this is the study of the platform with two elementary modules. So these are numerical results. And we see here that the optimum for an optimum is with 7 supports. It's not a great gain in the number of supports, but it's necessary to ensure not so important vertical displacement, and also not so intense variation of tension in the elements of forces. And we see here for solutions like that, that we have too many forces after loading. We are going beyond the yield strength for the cables, and even the buckling strength in compression for the struts. And last illustration of what we have to do in design is the study, the analysis of a platform made of 4 modules. So a platform of 6 by 6 meters. And here we have not so real sharp distinctions, but the possibility to work with only 12 supports instead of 16, which will be the simplest solution by juxtaposing each module with these 4 supports. Here we can go down to 12, even 10 if we accept some minor displacement and and increase in internal forces. Okay, so after the figures, I show you what we did actually, concretely. So we made a prototype at the MGC. So you have the different parts that constitute the nodes. So I said that we have 3 types of nodes. So these are distinguished by the inferior part of the node that connect to the cables and the tensioner. This is the regular node, which connects to the bars. And here, connection to a bar and 2 cables. And on the other part, you have the same common part, which is used to connect the layer cables. These are the cables that go in the 2 plane layers. And these cables are simply made of a cable with a fixed end. And for the border and corner cables, which are the diagonal cables that you see here, they are also of fixed length for the sake of simplicity. And they are, we are using here a different kind of connection. And for the tensioners, because they have to be, they have to allow the setting of the tension. It's simply a screwing system. And also on the practical parts, we have here the interface between the supports and the structure itself, using a translating system that allow to correct the imprecisions in implantation of the supports. And here a design of what you see in photo of the connection with the plates. Okay, so the assembly of the grid, you have here a detail of how we put in the cables and then the cap on top of it. And after having assembled the different nodes, the cables and the bars, you have here a module, which is constituted as simply as that. And here is another module in the folded configuration. So you see here the gain in volume. And just a detail here on the additional, the 2 bars here, that are the additional substructure needed for supporting the deck in the corner. So here, an illustration of the deck. You see here that this is the substructure system, the isostatic system that is added afterwards. We have the same here. And then the structure is complete. And we also added on it, I won't go into detail on that, but we added a model of an accessibility equipment, which consists in being an elevator to ensure translation in the water for disabled. So after that, after the construction of the modules, we did some lab tests. So you have here an illustration of some study on the reconfiguration possibilities. We can do the smallest one is a 3x3 module, but we can go up to 5x3 dimensions. 3x3 module is something that weighs approximately 20 to 25 kilograms. But if we accept additional weight, around 30 or 35, we can go to larger modules, which is also a good thing because you can cover a lot more surface. And the reconfiguration, because it's modular, every layer cable is the same. Each bars are the same. We have the same tensioners. So we can just play like a Lego, dismantle a part of one module to connect it to the other and form any other module. So we did also some structural tests. You have here an illustration in the garden. So I was talking about the support, and you have here the detail of the device that allows to set it more precisely. You have here the tensioner. It consists in a bar with a turnbuckle that allow to reduce the length precisely. And the loading system is just simple. We did some punctual introduction of force and distributed forces using heavy weights. And we measured using a tachyometer the position of the nodes and on the supports. And also to set up the internal self-stress, we measured the shortening of the tensioners using the position measured by the tachyometers. And some results are, for example, the cartography of the vertical displacement of every node, and you see here the effect. And we used it to calibrate the numerical models that are used to do the design. But structurally, it works well. It's quite efficient. But we had also to test it in situ. So here are some pictures that show you the whole process. And the first process, of course, is to implant the supports. And the supports, in our case, are made by using sand screw anchors. These are some devices used to fix boats, small boats, etc. And we derive them as vertical support for our structure. So we have to make a key used by 2 people to insert it in the ground. And after that, we can deploy the module, which is very quick. The deploy and setting up of the module takes about 5 minutes, not more. And after that, we can take it because it's very lightweight and put it on the spot. And after that, put the deck plates. So in this first test, we couldn't put any more deck plates because there were problems with the implantation of the precision of the implantation of the supports. And after that, we did also some other tests here on open sea, on open coast. So we could tackle the difficulties to implement the sand screw anchors, and but we succeeded in putting the deck quite completely and the complete structure. So obviously this is not complete. These are first tests, but practical tests, and we have also to improve that by improving the guiding and motoring tools that allows us to implement the screw, the implementation procedure, and also we look for other experimental sites, which is not easy because all the coast is used for tourism. So in order to really test the solution and the effect of erosion, for example, we need a site with long or mid-term possibilities. But actually, we could demonstrate that we can implant a structure. We also have to test the modularity by implementing 2 systems and join them on the sea. And also think about the other structures, the equipment, etc. So in conclusion, by this presentation, I show you that we showed you that tensegrity stressors can contribute to this kind of solution for accessibility by being lightweight, foldable, and structurally interesting. And we can in this particular example, build some any kind of platform using the rectangular modules. And obviously, there is also some work, a lot of work to do with the supports, but this is another story that is going on actually at this time. So I will stop it. So I was looking for the hour. I took some time. So thank you for your attention. And now we'll proceed with the question and answers. Thank you.
Thank you, Julian. So now we will start with questions that you can write down on the chat. Ready for that? May I start also addressing some questions to you. So first, Julian, thank you for this interesting presentation. My first question would be for you. This is a part of a project already closed, or this is something done at the university that this will be serving as a practical, let's say, platforms for being deployed or being installed in several points in the coast, or this is something very singular from your side? Or what is exactly the root of this project? So who was supporting this project for being performed, apart from, of course, your research group?
Yes, I didn't talk a lot of that about that. Yes, we were supported by we are supported by our region, by public authorities. Region. We were helped also by metropolitan cities of Nîmes, La Région Occitanie, our region, and also supported by our university. This is what I am showing at this time. Yes, and this is a work in progress, in pre-maturation. It's not ready to be used, as you see, but we advanced. In proposing this structure, and the final destination, of course, it's also an open question. Well, open, semi-open, because we are targeting actually the local operators on the coast, the cities, and we are discussing with them to buy this solution using by the intermediate of a company, maybe, that is to be setting up. And this is the work of our valorization service in the university. Okay. So the economical model is not quite finished, because we have to convince people that this solution is good for them. And in France, the accessibility is a real problem. So we have behind us associations and disabled people to go to promote this solution. But also the public operators like the region.
Okay, so the idea is probably to install these platforms temporarily, during summertime, whatever, and then
yes, it's
because these are not ready probably for winter time.
No. It's by design. It's meant to be temporary, because we have to respect the coast. Oh. And this is good also because actually the possibility to be easily mounted or dismantled is actually an advantage of adaptability. And there are a lot of movements on the coast. By sometimes you have a lot of wind, a lot of waves, and so a lightweight solution like this is also adaptable for the coast, and also easily to set up by the bars or the private operators on the coast. And the hope is to make a solution that will be taken by these operators to get something more in their tourism offer by offering the accessibility.
Okay. So Then first question we received from Tomás Dalda, and this is also linking up with my question, the next question that I have for you both. Tomás Dalda is asking, are the formations the limitations of this system? So I think for tensegrity structures in general, for large light on footbridges, large light or spans, I think Thomas meant to say. So for large spans. And my question is, do you think, both of you, do you think that tensegrity is only oriented or almost only oriented for smaller structures? Because so far we didn't see like any big projects for developing tensegrity systems, so to say, on big structures. So let's say domes, footbridges, bridges. We only saw one good example from Valen that he presented here. And also, let's say, smaller structures in general which are using tensegrity, but not like big projects are expected to use this structural system. So which are the problems there? So deformations, materials, complexity of installation. What do you think are the problems?
Well, I think there are many challenges that we have to accomplish, and we have to analyze in depth. About deformations, yes, that's one of the main problems, but they can be minimized by using more elements, more tensed elements, by instance, or by changing the topology of the structure. However, maybe it's more difficult to control the vibrations. It's easier to control the deformations than the vibrations, and there are many studies trying to minimize that effect on this kind of structures. As you see, well, these are very shakily examples, and whenever you build them with proper construction materials, you can have more efficient structures, as you've seen in Julian's presentation. I don't know if we will see many pure tensegrity structures in the future for big structures or for large spans, but I'm sure that they will be they will start creating hybrid structures using this kind of principle in order to add more resistance in an aesthetic way to conventional structures. That's what I think, and that's some of the research groups that are working on that now are thinking about that. But we don't need to forget that one of the most promising applications are in space, and there the vibrations and the deformations are different.
Okay. We have the next question. So we will, just to inform you, we will probably be here 5-10 minutes more for answering the questions of the audience. So we are like using more than 1 hour, but only 5-10 minutes for those that are interested in continuing. So one question is, how do you increase the safety factor on these structures? So this is one question. And the other one from Jose Castro, what about structural redundancy? Do these structures provide it? So safety factor and redundancy. So,
yes, increase the factor of safety. Well, you do the yeah. Because in the design you have to take care of the self-stress, initial self-stress that is usable to get the rigidity. So actually, when you self-stress the system, you consume a part of the capacity of the tense elements already at the beginning, and then when you use the structure under load, you have an augmentation, an increase of this tension. So actually, this is, but we don't have many displacements. So it's simply just like pre-stress structures. it's a superposition of an initial state and operational state of internal forces. So to increase safety, you tackle with dimensioning of the elements quite classically, but taking into account this superposition of an initial state of force and the effect of the actions. For the redundancy, because we have a lot of cables and you can be afraid to lose a cable by cutting it, of course, but it's like in other kind of structure. If you remove something in a classical structure, you have also problems. Actually, effectively, cables work in just one way. So you can't have the same redistribution possibilities as in classical solutions. So the redundancy is ensured by having complex tensegrity systems with a complex self-stress states. Many cables, like Valen said, have redundancy in cables, maybe, mainly.
Probably one question from Jose also is, what is happening if you cut a cable on your modular tensegrity structure? So the structure is collapsing, or this force is being distributed through the other cables and it can resist. So you will need to cut out 2 cables instead of only 1. So which is the level of redundancy in this simple?
The level here is 2. Is, in the elementary module, there are 2 self-stress states, so you have to cut 2 cables.
Okay.
But if you cut one, you loosen the system because you lose some internal forces already, but you have some redistribution. It depends also on the cable. If you actually, this kind of topology is fragile. If you have an event on the border cables, it's a problem. It's If you have an event on the tensioner, it's less a problem because you can have redistribution with a neighbor tensioners.
I don't know if I can add something. For giving an example, in this structure, I don't know if you see that the end of this strut is connected to the end of this strut, where just one cable, but we don't have any connection between this strut and this strut. We could add additional cables. The pretension state will be more complicated, but that will give redundancy to the system. Mm-hmm. More cables you add, more rigidity, but it's also true that that would be more difficult to calculate the pretension stress. So, well, that the possibility exists, but it has to be analyzed.
Okay. Let me share my screen. I would like to show you like an structure that was a result of our last presentation. So can you see my screen now?
Yeah.
Yes.
Okay. So this is a structure done for Concéntrico Festival in Logroño, a city in Spain. And it was presented by an artist. So he is not architect. He is not an engineer. He was an artist working with structural systems. And since, I don't know, 10 years, 8 years, he is like doing this kind of structures, playing a little bit with tensegrity. And I would like to have your opinion on if something in this direction can be used also as a construction structure, so architectural structure or even civil structure, like applicable in a bridge in an easy way. So of course, we know already that tensegrity structures have their own problems, but what do you think about having these applications with simple materials in a relatively fast construction for serving this? So one example is what you have presented, Julian, and the other example is this tensegrity structure, which appears to be very simple, but I assure you that this is not.
Well, I know the example because I know Jordi Gali, and his works are amazing, even if he's not an engineer or an architect. And well, he has some other examples that are also very interesting. And doing something like this, I think nowadays we are not ready for adapting that to a let's say, resistant structure. But it could be added to a architectural system in different ways. As George Slide used to say, Tensority is food for thought. And this is one of the examples that we should take into consideration in order to include it to architectural projects or architectural designs. I don't know what Julian thinks about it.
I wanted to have a view on the structural part. I don't see that as a real tensegrity, because what we don't see is maybe anchors on the both sides, or maybe thanks to the heavy weights on the ground. It's a sculpture that is put on the ground by many. And I don't think if it would be be in shape by itself in the space, which is something that is quite a general rule to have with tensegrity systems. A tensegrity system must have its shape by itself in the space, like inflatable. And so what I saw on this sculpture is more of a tense system that exists also in structural engineering. You have some you have cable beams in you see in a facade, in a roof, in a glass facade, which are on the same principle with cables and struts perpendicularly. So some application of what I saw exist already.
Mm-hmm. So I think my personal perspective is that we can go, or engineering in general, structural engineering can go for these kind of hybrid structures. So if I show you some examples from Slide's office, then this is, of course, it seems to be tensegrity structures, but these are not. No. According to Valen's concept presented here, these are not tensegrity structures. Partially, maybe we can consider them as tensegrity structures, but they are not. Honestly, I don't think that we are ready for having tensegrity structures in a big scale so far because of the materials. Probably if we are able, or in, I don't know, 10 years, 20 years, we are able to develop like materials with super properties or super flexibility, super resistance, then we may have this kind of structures in a bigger scale. But at the moment, this is not possible this will be possible, but very expensive, and they will be not very competitive with the other structural types. But
I agree with you. Maybe we are not ready for that, but these kind of webinars are very important and a very good starting point for somebody to start getting to the subject and starting analyze different proposals. And we weren't ready for the electric car 10 years ago, and now there's many people with an electric car. So time evolves, the structures evolves, the research groups put things on the market, and I think that projects like Julian's are very important to give more chances to this kind of structures, and hopefully in the future we can say that we have large span tensegrity structures or big tensegrity structures.
Yeah, for sure.
I'd say that we have some large span structures that exist that are, you know, the cable domes, Valen, false tensegrity, but they are very nice large span structures formed by bars and cables and pre-stressed. Something that is self-stressed and self-shaped like that. Okay, it's difficult because we have you have some struts and the buckling problems. But there are some interesting topologies to be explored also, and why not? In the case of food bridges, where to answer a question, yes, tensegrity systems are quite flexible. Well, not flexible, but soft, not rigid.
Adaptable.
And, this is the same as in classical food bridges, which are dimensioned on the vibration aspects.
Okay. So I don't know if there are more questions. Thank you, Julian. Thank you, Valen. If there are no other questions, maybe we can close the webinar, because it was reviewed to have 1 hour only. Then we have 75 minutes. Some of you have some questions. There is someone else there. Well, anyway, thank you to the both of you for joining, for presenting, for giving us a lesson about Tensegrity. So one more in the theoretical direction, the other one more in the practical direction. Thank you to the audience for joining us and sharing this evening with us. And thank you to the FIF for organizing this webinar. So have a nice evening until next time. Ciao.
Thank you.